Hello everyone. Welcome to this course of chemical crystallography. This is the week 8, and as all of you are familiar till now, so if you have any questions about this course or anywhere you are stuck, I request you to please ask your questions. Please post your questions in this Ask a Question tab in the SWAYAM portal. And today we will be discussing about this assignment 6. Since it is already past your due date, so today we will be discussing the assignment questions here. This assignment was relatively very easy. So the first question was that can we collect, so this was a true and false question, that can we collect more number of reflections using a molybdenum source compared to a copper source for the same crystal. So to answer this question, so we have this formula, so which was taught to you by the professor this week, that if n is the number of reflections which is collected, then the total number of reflections n which is collected is actually governed by an equation or a formula. So this is the formula where you can see that this 4, 3, these are all constants, and the variable is this lambda. What is lambda? Lambda is the wavelength of radiation which is used for the X-ray diffraction. So it is dependent on this, on the wavelength that is, if we use copper, then the wavelength K alpha 1 of copper is 1.54 and that of molybdenum is 0.77. So if this is in the numerator divided by the volume of the reciprocal cell. Now since it is in reciprocal cell, if we go to direct cell, then it will invert and we will get the final, and if we solve all these constants, we will get the final equation, something like this. As you can see here, the number of reflections has become inversely proportional to the wavelength of the X-ray radiation used. So if we use copper K alpha radiation and molybdenum K alpha radiation, so for an orthodynamic system with the same volume, you can see here this is 1600 angstrom cube. Then if we use copper K alpha, we can collect, you can see the number of reflections as 146, this is 14,600. However, for the same system, if we use molybdenum, then the number of reflections drastically increases to 1,49,000. Hence, you can see the importance of using molybdenum source compared to a copper source. Hence, this will be true that if we use molybdenum, we can collect more number of reflections. So this was the second true and false question, that depending on the unit cell parameters, one has to choose the detector distance. So this is again true, because as you are familiar with, where the professor has demonstrated the use of the Brugger 2 diffractometer, you can see the importance of choosing the detector distance. So these again, the lattice parameters may change during data collection from 300 to 100. So 300 Kelvin means this is a quite higher temperature. So this is in Kelvin. So this is actually room temperature. So room temperature is 298 Kelvin or 25 degrees centigrade. Hence 300 Kelvin can be considered more or less as room temperature, whereas 100 Kelvin is negative, negative temperature. It is quite low. So when we are, if we take the data at 100 Kelvin, which this means in the machine, we have to go from room temperature to low temperature. So while going to the low temperature, two things can happen. Firstly, the unit cell parameters, right, the ABC, the alpha, beta, gamma. So these unit cell parameters may change a little as a result of the change in the interplanar distances between the molecules or atoms in the crystal lattice. Because of that, the lattice parameters may change. That is one factor. Second factor is there might be a phase transition. While going down at a certain temperature, say around 200 Kelvin, that particular system for which you are collecting the data may undergo a phase transition, due to which the lattice parameters can change. So this is again true. Then a symmetric center is always added to the diffraction space, regardless if whether it is there is a symmetric center in the internal crystal structure or not. So by now you are very much familiar with this Friedl's law, right? This is again true because if there is Friedel's law, which means intensity of HKL reflection will be equal to the intensity of H bar, K bar and L bar reflection. Hence, whether the crystal structure is centrosymmetric or not, the diffraction space is always centrosymmetric. So now we have come to this question that the atomic scattering factor will fall off rapidly in which cities. So you can see this plot. So what is this plot? So in this plot, so this is the variation of atomic scattering factor. So what is the definition of atomic scattering factor? So atomic scattering factor is denoted by the letter small f. It is the amplitude which is scattered by an atom divided by the amplitude which is scattered by an electron. So as the scattering angle increases, the f reduces below the value of z due to more and more destructive interferences between the scattered waves. So in the question there were three options given, right? The O2 minus, neon and the silicon 4 plus. So as you can see, all of them will have the same atomic, so we have the same number of electrons, which is the z. So if we start from there, then we increase so if we plot this atomic scattering factor, okay, with the angle. So what is this? So this is the scattering angle which is normalized by the wavelength, because we can take in like copper or moly, so it is just normalized with respect to the wavelength, and we see that the silicon 4 plus will fall off much less rapidly than O2 minus. So here you can see, so this is actually taught in this atomic so this from here you can see that this one will be the correct answer. And then so we have the next question, that which of the following is not related to structure factor. So from the atomic form factor we come to the structure factor. So what is the structure factor? So structure factor is basically a mathematical description of how a material scatters incident radiation. So structure factor is basically a mathematical description of how a material will scatter the incident radiation, and it is valid only for systems with long range positional order or crystals. So if you take a polymer, so a polymer can have a short range order in some places or in some regions, but a polymer will not have a long range positional order. Hence you cannot determine the structure factor there in case of polymers. So there is an equation also for structure factor, as you can see here. So this structure factor equation relates the amplitude and the phase of the beam which is diffracted by the HL planes of the crystal to that produced by a single scattering unit at the vertices of the primitive dimension. So what we do is here, so to understand this equation, we find out the structure factor for a given HL plane. For example, you can find out the structure factor of suppose say 100 plane or 001 plane. So why do we consider planes? Because in crystallography the idea which we follow is the Bragg's law, right? So what is the core of the Bragg's law? So what is the core of Bragg's law? So the Bragg's law sees or rather Bragg himself, he saw the crystal as composed of planes with electron densities which we solve to get the atoms. Hence to find out the structure factor of any plane, say 100 plane or 010 plane or 001 plane, so we can find out the structure factor of any plane, and so where we will sum for any plane the structure factor, we will sum over all the atoms. So this Fn is the atomic form factor, small f, right? So you can remember that the small f is for the atom, atomic factor, atomic form factor, and the capital F is the structure factor. And summation over this HKL and the XYZ, which are the coordinates, right? So this was the question. So this is a very interesting question. You had to find out the structure factor of the 001 plane in a BCC system, right? So I hope you have enjoyed doing this. So here I have not solved it fully. So as you can see, at first what we will do is we will write this structure factor equation, okay, and then if we take a body centered lattice, it means that the two unique positions are this 0, 0, 0, which is the origin, and then we have an atom at the center of a BCC lattice, right? So there the position is half, half, half. Hence we will use these two as HK. So we will use these two for as here 0, 0, 0 and this half, half, half. Okay, and then we will try to find out the this structure factor for this plane. So I have left it blank. I will discuss it in the next live session, okay, how to solve it fully, but I will discuss it if you are not able to do this, because after I have to just solve this equation from here. So then this next question was that what is the limiting sphere and the sphere of reflection respectively. So as you can see here, if we put this, if this is the X-ray beam which is falling, and we have the crystal centered around somewhere here, then the sphere of reflection image where the evolved sphere basically is this one, the smaller one, and you can see the radius of the evolved sphere is 1 by lambda. This is why for molybdenum we have larger sphere than copper, right? Because molybdenum the lambda is smaller, so 1 by lambda will be larger. So this evolved sphere is this sphere of reflection with radius of 1 by lambda, and the limiting sphere is has this radius of 2 by lambda. Okay. So now this question, that what will be the data collection for orthorhombic system? What is the system of data collection for orthorhombic system? So to understand this, we will come here. So this is an orthorhombic system. However, so if we look at the crystal systems, we first have the triclinic, right, where there is like no symmetry. Then from triclinic we have the monoclinic, and then compared to monoclinic, orthorhombic has higher symmetry. So before discussing about orthorhombic, what we will do is we will first discuss about monoclinic. So there was also a question related to the monoclinic system, right? So we will first discuss about this monoclinic system. So if the crystal is monoclinic, which means there is a twofold symmetry in the system, right? Triclinic means there is a one-fold symmetry. Monoclinic means that there is a twofold symmetry in the system. So if the crystal is monoclinic, then we will have a twofold axis, and it is considered that the B axis is the unique axis. So you can see then in the reciprocal space the B star will become a unique axis. So if we rotate along B, that is along this K, then if it is symmetric, then there is twofold symmetry, then it means that the intensity of HKL sorry, the intensity of this IHKL will be equal to the intensity of minus HK minus L, right? Because of the twofold symmetry. Because of this added symmetry, so what will happen? At first we have Friedel's law. Friedel's law states that IHKL is equal to I minus H minus K minus L. This means from our full sphere we are already reduced to one hemisphere of the evolved sphere due to Friedel's law. Now further, what we have is, if there is a monoclinic system, then if we apply this twofold, so we have this intensity of IHKL which is equivalent to I minus H minus K minus L due to Friedel's law. Now if we apply the twofold parallel to Y, what will happen? Intensity of HKL is equal to intensity of minus HK minus L. So this is the term here. Now if we apply Friedel's law to this, because Friedel's law will also apply to this, right, then these three becomes equivalent to the intensity of H minus KL, right? So all these terms become equal, but what are not equal is these two, that is I minus HKL. IHKL and I minus HKL, we do not have any relation between them. Then these two are my unique reflections, my unique intensities. Now if I apply Friedel's law to this, I will get H minus K minus L. Now if I apply the twofold here, so then I will get the remaining, right? But what is important here, the important thing is that the intensity of IHKL is not equal to the intensity of minus HKL. So I hope it is clear to you. Then sorry, so for this question, this is actually a straightforward question coming from here, that these two are the not equal or the unique reflections. So we have this as the correct answer. And then for the orthorhombic system, data collection for orthorhombic system is reduced to which fraction? Here there are, for orthorhombic crystals, we have three mutually perpendicular two-fold rotation axes, right? So intensities of all these will be same. So you can just figure out, then it will further reduce from a quadrant to half of a quadrant, that is one octant. So I will if you have any doubts from here, so I will be available next week from that is on the coming Saturday, so which is I think 24th, right? So from 3 p.m. So if you have any questions, please let me know then. Okay, so thank you.